So, hi everyone. I am Bernice. I am a software engineer. I am based in Nairobi, Kenya. And yeah, I hope everyone is enjoying the conference. We'll go ahead and start this talk on adversarial attacks. So, yeah, so we'll begin by exploring what adversarial attacks are. Then we'll see some examples. And after that, we'll see how they're done or how you can generate an attack. Then we'll explore why you should care about the adversarial attack. And obviously, I think the talk wouldn't be complete without talking about the defenses. So yeah, let's get started. So basically, adversarial attacks are attacks where you create a very subtle perturbation and add it to your input, and then that causes the model to give an incorrect output during inference. So for instance, if you have a classification model, if you change the input just slightly, then the model, which could initially give an accurate prediction, gives an incorrect prediction, but without the additional perturbation, the model still has gives accurate predictions. So we'll just see an example, an example in computer vision for simplicity's sake. So for example, here you see we have an image of a cat. Obviously, you can tell it's a cat. And then for some reason, the model predicts it's a dog, even when obviously I don't think this change makes anyone here think that it's a dog. We can all see it's a cat, but for some reason the model thinks that it's a dog. So you might be wondering, how do you trick or fool the model into believing that this is a dog? And yeah, that's what we'll be exploring in the next section. But first, let's also see examples of adversarial examples in LLMs. So in the first example, you can see that the sentence is perfect performance by the actor, and obviously the sentiment analysis model predicts that that's a positive sentiment, which is true. And then the second one, so I think I didn't mention that the input that is perturbed is called an adversarial example. So the second sentence, the one that says spotless performance by the actor, that's an adversarial example. But obviously, to us humans, we can see that those two sentences have the same semantic meaning or convey the same idea, right? You know that perfect and spotless are both positive things to say about someone, but for some reason, that one word causes the model to change its prediction. Then in the second example, this is actually quite interesting because another idea of adversarial attacks is that oftentimes they will be imperceptible to humans, in the sense that when a human looks at those sentences, or in our previous example about the computer vision example, you can see, as a human, you can't tell that this input is different from the previous, from what a normal or a proper, an malformed input looks like. So in this second example, where we have the first input is send money to account 1234, and then so the attacker somehow finds an imperceptible input that someone wouldn't see, but to the model the input is if say I type on prompt ChatGPT, I'd send something like send money to account 1234, but it would get the input of send money to account U plus, you see the additional text, and that would cause the model to translate it very differently, such that eventually it becomes send money to account 4321, and yeah, then there are other examples, but the idea is the same. So yeah, those are examples of adversarial examples which would help us fool or trick the model. Yeah, then we can move to... Yes? All right. Okay, yeah, let's move to... let's explore types of these adversarial attacks. So there is white box attacks. In a white box attack, the person, the attacker knows everything about the model. You know the gradient, you know the hyperparameters, you have access to... So basically this would be, for example, on an open source model, where you have everything, you know the architecture, you know that you have the data set that was used to train the model, so it's easy for you to somehow reverse engineer and get an adversarial example. Then, as you've guessed, obviously there'll be black box attacks. And so under black box attacks, the attacker doesn't have as much information about the model. You're relying on the output. So for example, in a score-based black box attack, that would be the probabilities that the model gives. Say for example, it's a classification model that would predict, like, it's confident by some percentage that this is a given input. So you'd rely on that. So say it says it's 93% confident that it's a cat, 10% it's a dog, that kind of thing. That's a score-based black box attack. Then a decision-based attack is where you just have the final output. Like, you don't know what probability the model has to that, like, is giving to whatever output it's giving you. You're just relying on the output. Okay, yeah, then now let's see how adversarial attacks are generated. So basically, the idea is that we take advantage of the idea that when training models, you're usually relying on gradient descent to reduce the loss function. So when you're trying to create an adversarial attack, what you do is you rely on the same concept, but now you're trying to maximize, like, increase the loss function instead of decreasing it. So basically, you'd be trying to, so like, X remains, you're trying to like, it's like you're training for X, and normally you're usually trying to get the weights. So now you'd be changing X where X is our input. So yeah, for instance, in the example where we were talking about the imperceptible characters, the attacker would try to do a gradient guided search to find what characters will make the model make the wrong prediction. So you already know that you wanted to make a wrong prediction, then now you're just guiding, like, you're optimizing for it to make the wrong prediction. Yeah, then now let's see why we should care about this, and like why adversarial attacks are something we should consider when deploying our machine learning models. So one, obviously we know that, okay, so for right now, adversarial attacks have been something like a vulnerability that's known about neural networks. They're not specific to LLMs. This has been known for, I think, since like 2010. Researchers have been trying to figure out different attacks, and also with attacks, people come up with defenses that are also, people penetrate the defenses, and it's more of a arms race in terms of attacking, defending, that kind of thing. But it's good to know that this is a vulnerability that neural networks have, and also LLMs are perceptible to this. Then as LLMs become more used and in real-world applications, and also they are becoming more agentic in the sense that we are using them to do more things other than just prompting them and that kind of thing. We're integrating them with other systems. It's good to know that they increase your attack surface for your system. If you integrate an LLM into your usual software system, it means you're also introducing this as an attack surface for your system. Then, yeah, the other thing is that adversarial attacks have been known to be transferable in the sense that given that currently most models are trained with similar data, they have similar architecture, especially LLMs, they all are like a derivative of the transform architecture. The fact that you can design one attack for an open source model and then use whatever adversarial examples you get and use them on a closed source model, then they still work. That means, like, that shows that they're transferable. And so I think it's one of the reasons why people should care and like be cognizant that there are such attacks on LLMs, since most of the times people somehow think of security as an afterthought, especially in the machine learning space. Then obviously let's go through some defenses that you can implement for your models. One is sanitizing input. I think I hope some of you are software engineers here. You know that you need to sanitize input. You can never trust the end user. They will obviously, they can easily give you input that your model can't handle, or rather your system can't handle. So it's important to sanitize the input and ensure that whatever your user is giving is giving us input your model can handle, or throw an error and tell the person that they need to change their input. Then the other thing you can try is paraphrasing, especially now for LLMs. If you think that whatever input the user has given you is likely to be an adversarial example, then you can try paraphrase before returning before making inference. Then what the most effective so far, or what's considered the most effective in the industry as of now, is adversarial training, which is after you've trained your model, now you create adversarial examples and use those adversarial examples as part of your training data to make your model more robust. But this comes with the caveat of it's likely to cause your model to have degraded performance on your previous data set where the accuracy was probably high. If you include adversarial examples, then your model is likely to have some decreased performance in a sense. Yeah, so I think we'll conclude that. And I think my main point would be to insist on considering security for machine learning systems, because I think people think of it as an afterthought, or security is rarely considered in machine learning systems or AI systems. So I think it's one of the things I think we should all be cognizant about and think about when deploying our models. So you can scan this, then it goes to more resources, or rather references that I used when coming up with the talk, and more papers that people have done around adversarial attacks and adversarial examples. I think you can get more information from the URL. Yeah, I welcome questions, comments as we. Thank you.
Okay, thanks. We do have a couple of questions.
Okay.
From Slido. So the first one is, how can we implement input sanitization or paraphrasing against attacks towards image recognition, if you have any?
Okay, interesting. For images, or for images? For images, people tend to have a separate, it's like you have two models, and then first it's like you will infer from the two models and try and determine whether the initial image is an adversarial example. So you'd have your main model that you usually do inference from. Then the first model is just it's basically just for sanitized input in the sense that you're making a rough guess of whether this is an adversarial example or not. But I think the other thing about adversarial examples is that it's a very expensive thing to generate. So that's among the reasons why actually people aren't as worried about them, because you know that the attacker will need so many resources to generate it. But still, I think in security, the thing is the attacker only has to succeed once. So you might think it's expensive, but if they succeed once, then that's it for the defenders, I guess. Yeah.
Okay, the second question is it possible to sanitize input to an LLM? And if it is, how would you do it?
So, for example, you'd decide that for instance, when we were looking at the imperceptible characters, you'd have your model only take for example, you only take UTF coded data, right? So if someone gives input that's not UTF coded, then for example, you don't support the kind of encoding that the person is trying to present to your model, you just reject it and give a warning of, we don't support this, or try change your input, that kind of thing. So that's one way to go about it.
Okay. Third question, do you think having many open source LLMs would benefit or not the security of these models with respect to adversarial attacks?
That's, I guess, a double-edged sword, because we need open source models so that we can explore the vulnerabilities, because then again, if say they were all closed source, then we probably wouldn't even know about this, right? But the fact that they are transferable then now brings up the question of, do we want to open source more, which would also risk for the closed source ones? But I think I am all for more open source because I contribute to open source every now and then. So yeah, I am all for more open source.
Okay. How can we discover adversarial attacks except when it's too late?
That's why we need to defend before we even discover them, right? I think it's more of you, like you can't really detect it before, like if someone sends you an adversarial example and like your model takes up that input and returns, or rather, because sometimes you'll even find adversarial examples that are just meant to make your model, like to decrease its availability. It's not even to make a wrong prediction, but just to make it take so long or like use so much compute when trying to make inference because of how much like the kind of encoding that the person has done to the example. So I think if other than sanitizing your input and like all those things we've said, like making your model robust through adversarial training, when the attack actually happens, I think I don't think you can detect it until it happens. Yeah.
Okay.
Maybe we can take questions from the room.
Okay. A lot of questions live. Is it possible that vulnerabilities are transferred when distilling a model or performing transfer learning?
I think the main vulnerabilities, or rather like my hypothesis around the transferability of the adversarial attacks is that we are relying on similar architecture, similar data sets. I think that's where the transferability mostly comes from. I don't think it's from like fine-tuning, and because now fine-tuning, you're actually trying to make your model more robust and like more specific to a certain for a certain task, right? But like if it's underlying architecture and the underlying data set that was used is vulnerable, then even if you fine-tune, it's more likely to still to still be affected by the adversarial attacks.
Okay. There is one question. I mean, the talk was on LLMs, but if you have any hint on how can you sanitize images?
Yeah, I think
you answered like one before. Okay, we don't have any more questions on Slido. We have a couple of minutes, so if anyone wants to ask a question live, is welcome.
Yes.
Thanks a lot. It's a bit of a weird question. I will try to formulate it. Isn't the possibility of adversarial attack a hint that our model is maybe a bit too big or under-optimized? I'll try to specify. So I cannot give you an example with LLMs, but with an image, no human would ever take that second image for anything but a cat.
Yes.
Even if you lower the resolution there and if you transform it to grayscale, it will still be a cat to a human. While for a neural network, probably that well-cooked noise there, it's enough to confuse the network.
Yeah.
To me, this is something about the size of the space of the representation space of our data.
Oh, that's interesting because
so it's not really a question. It's just like something that itch my brain from the inside.
I think it's interesting in the sense that one of the hypotheses is that the fact that this none of us would obviously not confuse this for a cat. I mean, for a dog, means that there is what neural networks are seeing is very different from what we see, right? So, in a sense, people would say that the methods that how the model is learning makes it see that it's a dog because, like, before concluding it's a cat, there are some similar features that a dog has that are also similar to a cat. So, like, given how it learns, right? Like, say for images, it will start with like the lines, then learn each pixel as it goes, like that. Then finally the whole object. So before getting to like the whole object, all this whole learning process could also be influencing its decision that it's a dog. But I think it's a very nice thought to suggest that maybe because we have such a big representation, it influences the likelihood of the model getting tricked. Yeah.
Thank you.
Any more questions?
Did you just say the model getting tricked? Is that what your last? What your tricked?
Yeah.
You can trick a person, but
Well, but could you trick a person to think this is a dog?
well, no. What I'm asking is that when I look at that, it seems like, oh yeah, that's a very clever way to trick a computer. But it seems to me that I can only trick somebody if they already have understanding, whereas this is not really tricking it. It's just the input and the output. The machine is actually working correctly. It's just not doing what we want it to do. It's just that there's something in the machine that we didn't design correctly. And does that make a difference to how we think about how we build and improve these
So I think
models?
the trick part comes at, if I give it this image, like the initial input, it says it's a cat, right?
Yes.
But then I change something little, then it says it's a dog. Then that means changing something little makes it, it's like I have fooled it into thinking, wait, this is a dog or something.
Yeah, sorry, I don't want to talk about the microphone. I'm not sure that the language of tricking and fooling is correct. It's giving, that. I don't know. It seems to suggest.
Are you suggesting, because are you suggesting that we should go for, because like another space around this is that people think of adversarial examples as a feature of neural networks and not exactly a vulnerability. So like you're saying, like instead of saying, it's something like that, I think there is,
We can ask ChatGPT what it said we should
what it thinks, whether we should say trick or fool. Okay. But there's a very nice paper around, I don't remember the others, but I hope it's in the list of resources around that we should consider this as features of of neural networks instead of thinking of them as a vulnerability. Yeah. Okay. I think
Sure.
we're not out of time.
We have one more question.
Yeah, we still have time.
Yeah, hi. I was thinking about this from a geometric perspective. Like we have data representation spaces that have hundreds or maybe thousands of dimensions, models with billions of parameters. So there is a lot of space, of the geometric space for like gray areas and ambiguities. So I was wondering if you think there is a way to like direct a model away from these gray areas, maybe like in the LLM example, maybe just slightly altering the input steers the model towards an area of greater uncertainty. So maybe there is a way to like instruct the model to, whenever it enters an area that is known to be ambiguous, just steer back into the closest, confident area. I don't know.
So I think now that would bring us to, do we want our model to generalize well, or do we want it to get stuck in like doing a specific thing? Because if we want it to generalize well, then we have to let it search its entire space. So, but I don't think people have explored that as a defense to this.
Because I don't want to steal too much time. just the point is that in such high-dimensional spaces, there is always room for more adversarial attacks.
Yeah.
There is always room to alter the input just slightly. In just a different way that nobody expected before. So you can sanitize your input. You can, what did you say? Adversarial training. You can train the model against specific attacks, but there will always be space for a different attack that nobody could have foreseen because it's a billion dimensions.
That's why the space is more of an arms race. Like the defenders come up with a new defense system, and then someone else is able to break the defense, and we keep going.
Infinite arms race.
Yeah.
Okay.
I think we still. Okay.